After watching the following videos, students will be able to identify enthalpy of formation equations and their specific qualifications in terms of standard state. And students will be able to utilize two different methodologies to calculate enthalpy of reactions from enthalpy of formation values found in various appendices. So let's go ahead and take a look at the enthalpy of formation value. So enthalpy of formation is represented by this delta naught sub F symbol here. Now, standard enthalpy of formation is the change in enthalpy from a reaction that forms 1 mole of a specific compound from its basic elements with all the substances in their standard state. And so what do I mean by standard state? Standard state means a substance that's in its pure form at 1 atm and 298 Kelvin. So if I have a situation in which I have reactants that are elements in their standard state that give me 1 mole of product, then the enthalpy of that reaction, the change in enthalpy of that reaction, will be equal to the change in enthalpy of formation. So what we need to understand is that the enthalpy of formation values that we obtain are all reported at a specific pressure and temperature, which is 1 atm and 298 Kelvin. And basically, these enthalpy of formation values are categorized into tables, as seen here. And basically, they're expressed in kilojoules per mole, and they relate directly to the substance or substances that are involved in the reaction, whether reactant or product. And when you're using standard enthalpy of formation values and you're looking for substances in the standard state, you're going to want to pick the most stable option. And the most stable option is going to be the one that has a enthalpy of formation value that's closest to 0, or that is 0, excuse me. So if we go over here and let's see, manganese is one of the reactants, right? If manganese is one of the reactants, in this case, this table has 2 options for manganese. It has manganese solid and manganese in its gaseous state. The manganese with the delta heat of formation, or enthalpy of formation, excuse me, value that's equal to 0, that is going to be your standard state situation. So now that we understand the standard enthalpy of formation tables and how to actually select the appropriate substances in their standard state, let's go ahead and look at a few more details. So identifying reactions that actually can represent the standard enthalpy of formation, we have to follow a few rules. First things first is that a reaction, in order for a reaction to be an enthalpy of formation representation, you have to have a single mole of product. The next thing you need to have is that elements used to make the product must be in their most stable form, and you must have a single product. So the quantity of your product, the number of products, as well as the elements utilized all dictate if the enthalpy of formation values can be utilized. So now, remember we talked about these delta H formation values. Now they can be found in an appendix, usually in the back of the book, and basically you can utilize these for calculations. We'll look at that in a minute. For now, let's go ahead and decide if the following reactions seen here actually represent a standard enthalpy of formation. Okay, so if we go ahead and we look at this first problem, okay, so first things first is criteria A, 1 mole of product. There is a single mole of product here, so far we're good. Okay, elements used to make the product must be in their most stable form. Okay, so if we go into the appendix, we're going to see that our sodium enthalpy of formation value, so sodium solid, okay, and our gaseous O2 have enthalpy of formation values that are equal to 0, okay, and because of that, they are in their most stable state. Okay, so we've facilitated that requirement as well, so the elements are in their most stable form, and of course we have a single product. So all 3 of the requirements are met here, so this is a standard enthalpy of formation equation. Now if we look at the situation here, Okay, and we analyze it. Okay, first things first is we look at how many moles of product. In this case, we have 2 moles of product. So we automatically know that one of our requirements are not being met. Okay, if we check our enthalpy of formation values for our elements that are being used as reactants, we notice that our potassium is in a liquid phase. We check that with the appendix, and we notice that that is not its most stable form. In fact, the most stable form is going to be in the solid phase. So in order to fix this and make it where this is actually a standard enthalpy of formation equation, we're going to go ahead and change out our liquid potassium for solid potassium, and we're going to divide this equation by 2 so that we get this overall equation here. Okay, and in this last example here, if we go ahead and we look at what is wrong with this one, well, first of all, we don't have a single product, we have multiple products, so requirement C is not being met, and of course that means that the elements, the reactants here are not in their elemental form. Okay, so we have lots of issues here. So if we actually flip this equation, we have a single product, we have 1 mole of it, all of the elements being used are in their most stable form. We check that with the appendix, and this is a standard enthalpy of formation equation. We will see that our most stable forms of our elements are going to correspond to enthalpy values of 0. So your delta H of formation values that you should see for the most stable state are going to... Solving for the change in enthalpy of a reaction can be accomplished utilizing delta H of formation values, so the enthalpy of formation values. And there's 2 options that we can utilize, or 2 approaches we can utilize when doing these calculations. So our first option is to utilize Hess's Law and our delta H of formation values from appendices in the back of the book. Okay, we're going to look at that, and we can also utilize this equation here along with delta H of formation values from the appendices to help us get our delta H of reaction. So these 2 approaches are slightly different from each other, but they should give you the same result. So what we're going to go ahead and do here is we're going to utilize Hess's Law to calculate the delta H of this overall reaction by utilizing the delta H of formation values associated with the formation of specific components of the overall equation. So in order to be able to do this, we need to have our individual thermochemical equations sum to the overall equation we're looking for here. So what we're going to do is we're going to manipulate these thermochemical equations. Okay, and in this specific situation, the first one needs to be reversed, the second one needs to be multiplied through by 3, and the final one needs to be multiplied through by 4. Okay, so when we go ahead and do this and cancel out anything that shows up on both sides, we end up with this overall equation. This equation matches the equation that we're solving for. So what we're going to then do is approach our enthalpy values. Okay, so we know that anytime we change a thermochemical equation, whether we change the coefficients by multiplication or division, or we reverse the equation, that's also going to impact the delta H value. Okay, so my delta H of formation value here is going to be being reversed. So the sign of whatever my new delta H value will be is also going to be reversed, hence the negative sign there. Okay, for my second and third options, notice I'm multiplying my delta H of formations by the same coefficient that was used to multiply the entire equation, so 3 and 4 respectively. So after I do that math, I'm going to go ahead and I'm going to plug in those numbers into the equation like this. So basically I'm going to sum all of my delta H of formation values for my manipulated equations to give me my overall delta H of reaction. Okay, so I go ahead and I plug all those numbers in, okay, to what I see here. Okay, and I get this final answer. So this is the simple approach with Hess's Law. Make sure you're paying attention to units in terms of grams and liters, in terms of the states of matter, as well as units out here. Okay, make sure that they all match up. Also, please make sure that when you are doing these problems on a test or a quiz or something of that sort, please make sure that you are showing your work, that you're indicating that, you know, a reverse or multiplication by 3 is happening. Show what's actually happening. please make sure that I can follow what you're doing, because if you get the wrong answer and I can't see your mistake, I can't give you partial credit. Okay, now this brings us to our second approach to solving delta H of reaction problems using enthalpy of formation values. So utilizing this equation, our delta H of reaction is going to equal the sum of our delta H of formation of our products minus the sum of our delta H of our formation for our reactants. Okay, and we're going to do this for this overall equation. Okay, so what we're going to do, guys, is going to be products minus reactants. Now, remember, each formation value corresponds to the quantity of the substance there. Okay, so if I'm forming CO2, right, in this equation, though, I have 3 moles of it. So I'm going to multiply 3 by my enthalpy of formation value. Okay, same thing is going to happen here, 4 times the enthalpy of formation for H2O. And notice these two substances are my products. Okay, so I've figured out the sum here of my products. I'm going to do the same thing for my reactants here. Okay, and I'm going to obtain these values from the back of the book. Okay, so then what I'm going to do is I'm going to plug these numbers in from the back of the book and calculate my final answer. And notice it matches what we saw in the previous approach using Hess's Law. Okay, now what I want you guys to understand is if you choose to take this approach, okay, you must make sure that you guys are setting up your equations before you plug any numbers in. Please do not just give me the scattered, disorganized math, because if you make a math error, I can give you 0 points, versus if you set this up perfectly and then make a math error, I can still give you the majority of your points.